What makes video games work? Video games today are very realistic and fun to play. My favorite video game right now is Fortnite. How do video games work? What's the science behind what might seem at first be magic? We can start to understand what makes video games work by going back in time to a period called the Renaissance in Europe. That's a time when people became really interested in reading math and science books, including those from ancient Greece and Rome. Before the Renaissance, painters made pictures like this. It's okay, but not very realistic. Then in the Renaissance, painters began to use math to make more realistic pictures, like this one called The School of Athens by a painter named Raphael. By the way, one of the Teenage Mutant Ninja Turtles is named Raphael. All of the Teenage Mutant Ninja Turtles are named after Renaissance artists. This picture is more realistic because it looks like the buildings and the people are going back into the distance. Renaissance artists used ideas like perspective and the math of fractions to draw realistic proportions, so things looked less like cartoons and more like real things. They used grids that divided their canvas into equal squares and used them to help measure out how things look to us in the real world. This picture here shows one point of perspective where we see everything moving back towards one point in the distance. Today, math is used by computers to make even more realistic images in video games. To see how math is used to allow computers to communicate the images and sound of video games, let's go back and see how people communicated in the past before computers. In the 1800s, Roger Clark was visiting parts of Africa, and he noticed the tribes would use loud drums to communicate with other people over a long distance. The drummers used two different drum sounds and combined them together to make sounds that were linked to certain words like "come back home." There are lots of sounds in the jungle, so people didn't always hear the drum words correctly. The messages often had to be repeated over and over again in many different ways, so at least part of the message could get through. The ancient Greeks used fire beacons on hilltops to send simple messages over long distances, telling people something important either did happen or didn't happen. For example, in the ancient Greek history, it was understood that when the fire signals were seen, it meant Troy has fallen, meaning a major city has been taken over by enemies. But with fire and smoke, signals, clouds, and the weather could interfere with another person being able to see them. All that changed after it was discovered that electricity could be made to run through wires. Samuel Morse came up with a system in which the buzz of electricity through a wire, when turned on and off, could be used to send a series of dots and dashes, which are short electric buzzes and longer electric buzzes. In the 1840s, he created the Morse code, which looks like this. In this code, for example, to send the letter A, the sender would make a short buzz called a dot with the electricity, and then a longer buzz called a dash. Someone hearing the sound made by the dot and the dash at the end of the wire would then write down the letter A and the rest of the words sent along the wire. The Morse code was sent over electric wires called telegraph lines. At one end of the wire, someone would use this device called a key, which was connected to the wire. The operator of the key would tap a piece of metal to another piece of metal and connect the circuit in the electricity lines to send a sound for a dot or dash. Then at the other end of the telegraph wire, there was a machine called a sounder. That machine, like this one we have here, was attached to the wire and would receive the electricity signal. Moving electricity creates a magnetic field, which would make these magnets pull down this metal bar, which would then make a little clacking sound, which would represent the dots and dashes being sent over the wire. Pretty soon, people realized that lots of information could be sent with systems that worked with switches that were just turned on or off. Like Morse code worked by just turning the electricity on or off. About 100 years ago in the 1940s, a man named Claude Shannon realized that if you set up lots and lots of electric switches, you could communicate lots and lots of different things by coming up with a code based on how different switches were switched. To make this easier to understand, let's look at the cool robot mouse and maze Claude Shannon made to show how the system worked. Shannon made a robot mouse that could only move in 4 directions: north, south, east, and west. It moved around each square of a maze, 1 square at a time. If its wire whiskers hit a wall, it tried another direction. If its wire whiskers didn't hit a wall, it moved ahead to the next square, where it would look again for the direction that didn't have a wall and move forward again until it made it to the end of the maze. The important thing here is that a combination of switches told the robot mouse which direction didn't have a wall in front of it. I also like playing this video game Minecraft, so I'm going to use it to show how this worked. 2 switches were used to indicate each direction. If the mouse could move north, both switches moved to the on position, on. If the mouse could only move south, the switches would flip on, off. The first switch in the on position, the second switch in the off position. If the mouse could only move east, the switches would flip off, and if the mouse could only move west, the switches would flip off, on. As the mouse moved around the maze, switches would be flipped to indicate which direction the mouse could move forward in. With all these switches already flipped by the time the mouse finished the maze, the next time the mouse was put at the beginning of the same maze, the robot mouse would walk straight through to the end of the maze, no problem. Shannon figured out that each switch could be considered one bit of information, as we saw with the robot mouse in the maze. With just 2 switches, you can indicate 4 choices in the case of the mouse maze. The choices were north, south, east, and west. So for every switch you have, you multiply by 2 to get the numbers of choices the computer can make with the numbers of switches it has. If you have 2 switches, you have 4 choices because 2 times 2 equals 4. Now, if you had an 8-bit computer, you'd have 8 switches. How many choices could that computer make? Well, it would have 8 switches, which means you kept multiplying by 2 8 times. An 8-bit computer could make 2 times 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 2 choices. When you multiply 2 times 2, you get 4. When you multiply 4 by 2, you get 8. When you multiply 8 by 2, you get 16. When you multiply 16 by 2, you get 32. When you multiply 32 times 2, you get 64. When you multiply 64 times 2, you get 128. When you multiply 128 times 2, you get 256. So an 8-bit computer can give you 256 choices. And if you had a 16-bit computer with 16 switches, you'd have 65,536 choices. So let's apply this to video games. When you play a video game on a screen, you look closely at the screen. If you look closely at the screen, you'll see thousands of little squares. Each little square is called a pixel. If you have lots and lots of switches in your computer, different combinations of these switches can tell the computer to make some of these pixels different colors. For example, one combination of switches can tell the computer to make the pixel turn yellow. Another combination of the switches can make the computer turn the pixel blue. And another combination of switches can tell the computer to turn the pixel green. And another combination of switches you might use when using a game controller will tell the computer to shoot at a target like this. Or your controller might tell the computer to blow up something like this. Computers today don't work on switches that look like this, but they still operate on switches, except now each switch is just a tiny connection between middle nodes that can be turned on or off. Today, millions of these tiny switches can fit on a tiny computer chip. So now even something as small as your phone can hold a supercomputer worth of switches. And you can even play Fortnite on a phone. Math helps make video games in another way too. This type of math is part of what's called chaos theory, which is a way of looking at the world to find patterns in what you might otherwise think is just random. Let's take an easy example by playing this game. Put 3 points anywhere on a page. It will form the points of a triangle. Then label each point A, B, or C. Now, we're going to set a rule for whether a roll of a dice means it comes up A, B, or C. Let's say if I roll a 1 or a 2, it's an A. If I roll a 3 or a 4, it's B. If I roll a 5 or a 6, it's C. Now, let's start putting a dot anywhere inside the 3 points. And now, all I'm going to do is keep rolling the dice. Whatever letter it comes up means I'm going to put another dot halfway between the last dot and the lettered point the dice tells me to move towards. So here I rolled a 1, and let's make a dot halfway between the last dot and A. Now I'm going to keep doing this over and over again. Okay, so I did this a lot of times. and we're just beginning to see a pattern. I could be here all day adding more dots according to these rules, but let's have a computer pick lots of random numbers and show what happens if I keep adding dots myself. Amazing, isn't it? What you might think would be a random pattern of dots that are everywhere actually comes out as a distinct pattern made by following these rules over and over again. We can use these same rules with a square. This is the pattern that forms with 4 dots in a square formation. We can use the same rules with a hexagon. This is the pattern that forms with 6 dots in a hexagon formation. So what do patterns like this have to do with video games? Well, a math expert named Michael Barnsley discovered the following. The math here is a lot harder, but basically these two triangles summarize 2 possible outcomes of another rule. Here you use a certain probability to make a dot near one of the corners of the red triangle. And with a smaller probability, the rule will have you flip over to make a dot near the smallest blue triangle. Now, every time you roll the dice, you follow this more complicated rule and see what shape you will make. This is a computer making the dots according to those rules. It's amazing to see what shape appears now. It's the shape of a fern. Here's a computer using the same rules to make a quicker and more detailed version of the same pattern. This shows how natural things have inside them certain math rules for making them. And because you can make realistic plant shapes like this using a few math rules, video game makers can use these simple rules to make lots of realistic looking plants with just a few computer switches instead of thousands of switches. So you see, video game makers don't have to draw these natural plants all by hand. All of the information needed to make them is a few simple rules of probability that computers can run over and over again very easily, so I can hide in a bush in Fortnite. That's my presentation on how computer games work.